Hey guys, I hope the viewing today won't be too different. I've just got a little I've got a little mount to hopefully give, so you won't be looking at the base of my neck and my torso the whole video. Uh, I don't want that to become a theme of these videos or uh, or anything. I want you to be able to see me as I'm talking because I know it's a more engaging experience. So I hope you enjoy this better. Let's get into it. So today we're covering exponents. Now I know I said we weren't going to get back into basic arithmetic operators like addition, subtraction, multiplication, or division, but I thought exponents would be important to cover again because the inverse, or the opposite, mirror image of an exponential function is a logarithm, and we're going to need to know that. I need to brush up on that, honestly, so I think that this will help us. You can't understand a logarithm without an exponent, or vice versa. So, exponential. Let's talk about that word. Whenever a pundit, maybe a media person, is talking about growth of something, and they want it to make it sound terrifying, they say that the growth of this thing, whether it be a disease or a stock market change, any number of things. If the growth pattern is exponential, they're saying it like it's terrifying. It's growing, it's growing, it's growing. Non-stop growth. That is kind of what an exponential function is. You're talking about a growth rate or a decay rate. And if you're in computer science and you're working with big O notation, maybe you're coding an algorithm or you're coding a program, and something is taking an operating time that's exponential, then your program's likely to crash because it's hogging too many system resources. So exponential is a word where it connotes something growing or decaying very, very, very rapidly. So getting into exponents, there are a few rules, which we're going to learn today to work with them and manipulate them, because they operate a bit differently than other numerals when you multiply them or add or subtract them or divide them. So today we're concerned with a couple of keywords here. So the base of an exponent. So that's that coefficient right there, that 2. I guess you wouldn't call it a coefficient in this sense. It's basically whatever we're told to exponentiate. So in this case, I have the problem 2 squared times 2 cubed. So just to get into what I mean by 2 squared or 2 cubed, what does that mean? You might hear statements like 2 to the power of 4 or 2 to the power of 5. 2 squared and 2 cubed are just the same way of saying that it's 2 to the power of 2 or 2 to the power of 3, respectively. So when you see an exponent, such as 2 squared, you're being told to multiply 2 by itself 2 times. 2 times 2 equals 4. So that's probably a bit of review for you. We're more or less coming here to find out what to do when we see exponents in problems, and when we learn how to factor polynomials, or working with polynomials, or quadratics. You're going to need to know how to manipulate exponents. So let's get down to the meat of it. So we have this problem here. What is 2 squared times 2 cubed? So we're looking to make sure we have the same base. The base here is whatever's being exponentiated. The base is the same. It's a 2. So your natural inclination might be to treat it like a multiplication problem, like it is, and I'm not sure what you would naturally want to do with the exponents. We'll see what to do with them properly, but your first inclination might be to say, well, 2 times 2 is 4. If you're multiplying exponents that have the same base, you are going to leave the base unchanged. Well, let me show you. So we're going to add the exponents here. The base remains unchanged. 2 squared times 2 cubed equals 2 to the power of 5. How do I know that? How can I be certain? Well, let's break it down. If we just solve the exponents first, right? What if we just solve the exponents first? What if we just said, what's 2 squared? Well, it's 4. What's 2 cubed? 2 cubed is 8. So we're being asked to multiply 4 times 8. 4 times 8 is 32. Now, will we get the same answer if we just, handle 2 to the power of 5th on its own? What if we just said, what's 2 times 2 times 2 times 2 times 2? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. You can see that it's proven that way. So that logic that we just applied to 2 squared times 2 cubed, that same logic holds with variables. So in the same sense that we solved that problem, x squared times x cubed would equal x to the power of 5. Now, it's very important to understand when you look at a problem, what is being exponentiated? What are you asked to exponentiate? So if I were to say 2x squared times perhaps just x cubed, what would that equal? Well, you would say, Taylor, you know what, let's just for argument's sake make that a 2x. I've changed the problem. It's 2x squared times 2x cubed. So maybe you're saying to me now, well, Taylor, I would not multiply that 2 by the 2 to get 4x and then whatever the exponent is. You told me not to do that. Well, look here at what's being exponentiated. It's the x. The x is the base. The 2's are not the base. The 2's we're still going to multiply by each other. So 2 times 2 is 4. And then let's handle the bases that are being exponentiated. You're treating that just like a multiplication problem. 2 times 2, it's 4. Pay attention to what is being exponentiated. And the way that that's going to be shown to you, if I were to say 2x, the entire thing is being exponentiated, well, that would be done with parentheses. That's to show that that square applies to both the x and the 2, not just to the x. But that's not what's happening here. So let's erase those parentheses. The base in this problem is x. 2x squared times 2x cubed is 4x to the power of 5. Right? Because you've added these exponents. In the case of multiplication of exponents with the same base, you're just going to add the exponents. 2 plus 3 equals 5. And that is the product rule. Hope you guys can see everything. So now we're gonna do the opposite. We're gonna divide exponents with the same base. So take, for instance, the problem that I've written down, which is x to the power of 7 divided by x to the power of 2. Division is the opposite of multiplication, so your brain should be saying, well, we're going to treat this in an opposite manner that we treated maybe the product rule. If that's what you're saying, that's correct. That's a correct assumption. So when you're dividing exponents with the same bases, you're going to treat the exponents in a way where it's subtraction. X to the power of 7 divided by x squared is going to be x to the power of 5. Now, let's mix it up a bit, and we're going to stick maybe a coefficient in front of these x's. A coefficient is just a numeric value that you're multiplying a variable by. So let's say we'll take 14x to the power of 7 divided by 2x squared. Same thing here. If you have those coefficients, divide them. 14 divided by 2 is 7. Don't subtract. It's very easy to get this coagulated in your head where you're thinking that you need to treat the coefficients the same way that you're treating the exponents. That's not the case. With the coefficients, just separate this stuff. Coefficient, variable being exponentiated. So we divided the coefficients. 14 divided by 2 is 7. We're going to treat the exponents, that x to the power of 7, x squared. We're going to treat that kind of its own problem. So subtract the exponents. X to the power of 7 divided by x to the power of 2 is x to the power of 5. Okay? Now let's get into the power rule. So this one's going to throw you for a bit of a loop, because you've seen this requires a different type of thinking. When you're wanting to perhaps multiply something, you're being asked to add it. When you're wanting to divide something, you're being asked to subtract it instead. The power rule, more or less, stays with our modes of thinking. So let's take, for instance, two variables, x, y to the power of 7. This 7, it's exponentiating both the x and the y. That's why there are the parentheses around it. We've been lacking parentheses in our previous problems because the exponent was only applying to one thing, whether it be a number or a variable. Now it's applying to two things. It's applying to both of these variables. So go ahead and break down the parenthesis, distribute that 7 to both the x and the y. Okay? Now you're maybe asking what to do. What do we do if erase this whole thing. What do we do if there is a coefficient in there too? In fact, let's really mix it up. So what I've written is, in parentheses, 7x squared, y squared. All to the power of 2. Everything in here is being squared. Okay? Everything in here is being exponentiated. Let's distribute that too. And this might throw you for a bit of a loop. So first, let's do what's simple. The 7 squared. 7 times 7 is 49. Now the x. We're going to treat this like multiplication. When you're exponentiating something in parentheses, you're handling it like multiplication, right? X squared squared was what we have. X squared is in the parentheses, we're squaring it again. So it's, if you see something like that, something is in parentheses, and we're being asked to basically add another exponent to it, multiply these. 2 times 2 equals 4. And similarly with y, okay, we have 49x to the power 4, y to the power 4. I know that's confusing because I've asked you to square the 7 and then take the x squared and multiply it by 2, and the y squared and multiply it by 2 to get x to the power 4, y to the power 4. If you want to deep dive that with me, we can get into the axioms that prove that and support that notion. But for right now, if you want fast, quick and dirty tools to solve exponents, we're remembering the product rule, the quotient rule, and the power rule. That, my friends, is how we manipulate exponents. So with exponents, there are 2 special cases I want to dive into, and these are quite easy to remember. So you're asking me what do we have if we raise anything to the power of 1? Well, think of it. Think of raising 9 to the power of 1. And in fact, this might be an easy way to think of any number without an exponent. Think of a invisible exponent power of 1 next to it. It's unwritten. In any problem, there is an unwritten positive 1 exponent. So if it's actually written, if someone is asking you what is x to the power of 1, x to the power of 1 is x. X multiplied 1 time. X multiplied by itself 1 time. It's just x. 9 1 time is 9. Anything to the power of 1 is the base. Any base to the power of 1, exponentiated to the power of 1 is the base. That's it. The other special case that we have is when we have a base to the power of 0. This one's also easy to remember. We'll take the same base as x and 9. Anything that is raised to the power of 0 is 1. The number 1. That's it. That's all you have to remember. Anything raised to the power of 0 is the number 1. So let's talk now about where we see this on a graph. What does it look like? And why, when we're modeling behaviors in the real world, is exponential growth terrifying? Maybe it's the coronavirus we're talking about, like new cases. The reason why it's not natural is because the growth rate is so explosive, right? So the linear function, you have something climbing up a smooth, steady ramp that's predictable and never changes, right? With exponential growth, it's for every change in x, every whole number change in x in this problem that we have here, f of x equals 2 to the power of x. With every change, whole number change in x, y is doubling. So you can see when that happens from basically x equals 1, y equals 2, x equals 2, y equals 4, x equals 3, y equals 8, and so on and so forth. If you're ever given one of those problems of, if I gave you a penny every day and I doubled that contribution every day, and so on and so forth. If anyone's ever asked you those kinds of trick questions and you've guessed, oh, I'd have $10 at the end of the week, and then the person is amused at your answer and tells you you'd have several million at the end of the month, whatever the case may be. It's a problem of exponential growth. It's doubling. So I always like to relate things back to computer science. Oh man. I always like to relate things back to computer science and tell you how it could relate to that. So, bits, right? A bit is a piece of computer architecture. A bit is a representation of data in a binary sense, right? So a bit can be represented as 1 if the piece of equipment is receiving voltage, or off, 0. So we're going to get into why this deals with exponents. So a bit can be represented by a 1 or a 0. It's Boolean, right? True, false, 1, 0. It's binary. Binary language. So you might have noticed that a byte, which is 8 bits, well, it can take on 256 different values, right? And that's just a string of 8 different characters. You could write 0, 0, 0, 0, 0, 0, 0, till all 8 values are 0, and it represents a 0. 0, 0, 0, 0, 0, 8 values, the last one being 1, represents a 1. So this is how a computer understands instruction sets, right? 64-bit operating systems obviously incorporate a lot more of those 1s and 0s into instructions. So I don't want to bore anybody. If you're not into computer science, that's cool. But if you have 8 bits here, let's just start with 3 bits, for example. Well, you could have, this one could be a 0, 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 this one 0, this one 1. When we get down to it, there are 8 different combinations of instruction sets that 3 bits can have. But why 8? Why 8? Well, it's every bit can have 2 different instructions, 0 or 1, true or false, yes or no, right? Binary. And there are 3 bits that we're talking about. It's just exponentiation. Therefore, there are 8 different instruction sets that we could give 3 bits, right? 8 different numbers, 8 different instructions. So another interesting thing about exponential functions, especially like the one I've written here, is that they're going to have horizontal asymptotes. And we're going to talk about asymptotes a little bit more later. When we get into calculus, they're all over the place. Trigonometry has a crapload of asymptotes. It's basically where a graph like this one shoots up into the sky, and I know that this one will approach a value and it'll just go on to infinity, basically, from this direction. But from this one, you can see how it flattens out, right? It looks like it's approaching 0, approaching 0, approaching 0, but never really gets there. Well, that's another thing about exponents. If we're on this side of the graph, right, f of x equals 2 to the power of x, well, what if I tell it f, like the argument I'm giving it is -1? Well, that's saying f of -1 equals 2 to the power of -1. Oh crap, there's a negative number in the exponent. How do we handle that? Well, that's the last rule I want to teach you. So a rule of thumb with raising bases to negative integers, or negative exponents, I apologize, to the power of -1, for example, we're going to stick a 1 on top as a numerator. It becomes a rational expression. and then whatever this base is becomes the denominator, and then the positive value, or the opposite value, right? The opposite of -1 is 1, becomes the exponent here. 1 over 2 to the power of 1. Well, you could just say 1/2. 2 to the power of 1, this is 2. So that'd just be, you could write that more simply as 1/2. So what if we get, let's say, 2 to the power of -3? Well, again, we're going to take that 1, put that as the numerator, and then the base 2 drops down here, and then we take -3, make it positive, stick it down here, again as the exponent. Well, you could solve that exponentiation, it would equal 1 over 8. 2x to the power of -3. So the only thing being exponentiated to a negative exponent is the x here. The 2, let's leave him alone. 2, because really when you write 2x, it's saying 2 times x. Well, this is saying 2 times x to the power of -3. Let's separate the 2, right? Simplify it. So we're going to say 2 times, well, from what we know about negative exponents, we can write x to the -3rd as 1 over x to the power of 3. So then it just becomes a simple problem of finding out what is 2, which can be written as 2 over 1, times 1 over x to the power of 3. Oops. 2 times 1 is 2. 1 times x to the power of 3 is x to the power of 3. It becomes 2 over x to the power of 3. So negative exponents, they can be a bit tricky. They always end up as a rational expression, okay? They always end up with a division sign, or, a fraction. So a couple of things maybe humorous things I want to leave you with about exponential growth, or exponents in general. So, that's a shitty setup for a joke. Anyway, there's a band called 1023 Megabytes. They haven't gotten a gig yet. Another thing about exponential functions, a pyramid scheme is a good example of one, right? So you've seen pyramid schemes collapse because it's not really selling a product, it's selling the selling experience to someone else, right? So you're the guy at the top, and you have to get 2 people to sign on to selling, what is it, Avon, or I guess Avon isn't a great example. There used to be something called Vector Knives in the hometown I grew up in, that they went door to door selling knives, or selling the ability to sell the knives to other people, right? There are a lot of pyramid schemes that actually don't have any product behind them. They're not selling anything. Maybe just a membership into something that doesn't exist, or, so on and so forth. But a lot of them do have products. But the point isn't to sell the products, it's to sell the experience of selling the products to other people, to bring them into the culture, right? So one person brings in 2. Those 2 people bring in another 2 people. Those 4 people bring in 2 people of their own. Right? On and on and on it goes, doubling with each time. Here's the first row, 1. Here's the second row, 2. Here's 4. Here's 8. Here's 16. Here's 32. Here's 64. Here's 128. Right? The thing about exponential growth and pyramid schemes in particular, if you're talking about a small town, when are you going to run out of available people that, number one, would buy into this scheme? And even if everybody did buy into the scheme, at what rung of this have you ran out of people to even sell it to, right? I mean, at some point, if everyone in the entire world bought into a pyramid scheme, you'd eventually run out of of people in the world to buy into it. So that's why those things are made to collapse. That's why the people at the top reap the most benefit. It's an example of an exponential function. It keeps doubling and doubling and doubling, and you eventually run out. And that might be a cautionary tale with coronavirus and why you don't want to see exponential growth. Or maybe you do. Maybe if you believe in herd immunity, at some point everyone will have caught this, right? Because if it's growing at an exponential pace, eventually that will overcome the medical system. Problem is, so many people will die in the process of that occurring, right? So you don't want to see an exponential growth pattern, especially in disease. So that's been Exponents. I hope you guys have learned something. Sorry about the editing. I had to actually refresh myself on how to handle negative exponents and different bases. So that's me being real with you. It's been a while it's been a year since I graduated. And it's good to refresh these things. So take care.